So the best way to do a derivative is what's going to force you to do the simplest thing possible. So by rewriting this, separating that 1/3 coefficient out in front, rewriting that so it's not fractional anymore, use that negative exponent. We can use the power rule very quickly. So watch what happens. This one, the 2 drops down in front, becomes a 2/3 x to the first. -3 drops down in front, multiplies by the -3, makes the 9. The power goes down by 1, so that's why it's -4. But when you plug in 1, and usually, I'm going to choose numbers that are nice to plug in, okay, because I'm not testing your algebra skills. Hopefully you're here in calculus, you know how to do algebra. I'm going to test more of your numerical, did you do this product rule, quotient rule, power rules right? Did you do those derivative rules right? So then that 9, don't make that harder than it has to be. All you have to do for that is just take your 9, multiply top and bottom by 3, and that's why you get 27/3 for a total of 29/3. Okay, so hopefully that wasn't anything too crazy, but you're going to have to memorize all of our rules. This doesn't go away. It doesn't go anywhere. It is something very important. 2-4 is nice because it just practices some of those rules. But now we're going to introduce our trig functions into the mix. We're going to learn some new rules related to our trig functions. I thought it was a complete repeat, but it's not. So anyway, so let's learn some things about our trig functions. There are rules that we're just going to need to memorize. There's no two ways about it. You just have to memorize this stuff. But I'm going to show you some things that you're going to have to memorize. This is just a result of the squeeze function. You don't have to know anything up there on top, but please make sure that if you see this limit, which is a 0 over 0, if you do try to plug in 0, there's no good way for us to manipulate it. This is one of those limits that you just have to memorize is equal to 1. And this is one of those limits, yeah, you do get 0 over 0 again, but you do have to memorize that that is equal to 0. So it's all because of the squeeze theorem that those two limits become what you see there. Now, it doesn't have to be thetas. We're used to seeing thetas by a trig function. It can be x's, as long as they match, actually. If it's sine of 2x over 2x, if it's cosine of 2x over 2x, it's always going to get the results that you see up there on the page. So it's just a new little extra piece to memorize. But it basically happens because of the squeeze theorem. You get two nice things around the sine one, and it always becomes 1, and then same thing you can do with the cosine function. But the result that I think is you're going to find kind of interesting. So let's look up here. This is our sine function. Remember how in the 2-3 notes we looked at what the shape of the derivative looked like? So think about it's increasing, it's increasing, it's increasing. And you see how its derivative is positive in those areas. It's decreasing, it's decreasing. Its derivative is negative in those areas. It's a 0, 0, 0, those horizontal asymptotes. So our derivative is 0. Do you recognize what this function is? It's the cosine. So it's kind of interesting that the derivative of a sine is equal to a cosine. So that's what you need to maybe highlight or write down, that the derivative of a sine is a cosine. So that's another fact that you have to memorize. So that just kind of shows you how, and they even do some manipulation here with the difference quotient using a sign. This is the sign sum identity we gave you last year, and they're just proving it. This is algebraically proving that it's equal to the cosine. You're never going to have to prove it. You just need to know it exists, that the sine's derivative is the cosine. Yes. It does not. So that's a good question. The cosine's derivative is not a sine. It's close. And let me show you. I think maybe on the next slide. The sine's or the cosine's derivative, it almost looks like a sine, but it's a sine that has been flipped. So like if you see a cosine graph, it looks like this. The derivative has to be a, so that's the cosine graph. The derivative is the sine graph flipped. So normally our sine graph is here, but our in this case, the derivative goes down here. For it to match up where the sine, where the cosine is increasing or decreasing, it's a sine flipped. So it's kind of interesting that does that. Now, one thing, a pattern that might help you when we go to start memorizing these things is that any of our trig functions that have a co on it, the word co on it, its derivative always has a negative attached to it. Okay, so that's a pattern. Any of our trig functions that have a co on it, so cosine, cotangent, and cosecant all have a negative on their answer. To make the derivatives line up, the increasing, decreasing stuff, it ends up becoming a negative. So you'll notice that the derivative of a sine is a cosine. The derivative of a cosine is negative sine. The derivative of a tangent is secant squared. Now, let me kind of show you. Do I show it to you anywhere? No. Why is the derivative of a tangent secant squared? Well, this is sine over cosine, right? Remember our quotient rule we learned the other day? The bottom times the derivative of the top minus top times the derivative of the bottom over the bottom squared. You end up getting, when you do that formula, you get sine squared plus cosine squared over cosine squared. What's sine squared plus cosine squared equivalent to? 1. And so you get 1 over cosine squared, which is a secant. So that's what happened to a tangent. Do you have to know that transition? No. Could you find it if you forget? Well, if you know that tangent is sine over cosine, if you do the quotient rule at any time, it does come out to be a secant squared. It's a long process. You'll see, look at how many steps. You would have to do the quotient rule. You would have to simplify it to this. Then you would have to simplify it to this, and then you would have to simplify it to this. So of course, it's much more efficient to just know that the derivative of a tangent is a secant squared. Okay, but these 3 facts right here, you got to get in your brain. I don't care if you say it 17 million times, if you write it down 17 million times, whatever works for you. Make yourself some flashcards. We're going to put those on our vocab list just so we kind of have them all listed in one spot. But you have to know the derivative of the trig functions by heart. So let's think of everything we know so far. We know the power rule. Power drops down in front, power goes down by 1. We know the product rule. First times derivative of the second plus second times derivative of the first. We know the quotient rule. Bottom times derivative of the top minus top times derivative of the bottom over the bottom squared. We know now the trig functions. Sine is a cosine, cosine is negative sine, tangent is secant squared. Now, there are 3 other trig functions, so we're not done. So you have to know more than that. But first, I would like to practice one of the ones we know. So y equals x squared sine of x. Let's differentiate that. Now, to differentiate that, the first thing I want you to get in the habit of doing is put a little dot between 2 things that it's pretty much impossible to really effectively kind of multiply down to something simpler. Okay, so put a little dot. That dot, I hope in your head, means multiplication, means product. So it's the product rule, okay? So we're going to have to do first times the derivative of the second plus second times the derivative of the first, and that's it. I was going to make it something more than it was. So the derivative of a product is first times the derivative of the second plus second times the derivative of the first. So x squared is going to be our first. Sine of x is going to be our second. Okay, so our second piece of the product, our first piece of the product. Okay, now we know how to take the derivative of an x squared. It's just 2x. We know how to take the derivative of a sine now. It's cosine. So we're going to put those pieces together in the formula. Okay, so it's going to be the first. You just write it down. Times the derivative of the second. You just write it down. Plus the second. Just write it down. Times the derivative of the first. Now, I tend to write sines and cosines in parentheses so that I don't confuse where the x that's with the cosine or sine, where it's sitting. And so use parentheses to kind of clarify what is doing what, okay? Everybody see how we got that derivative? Did we have to do anything funky with, f of x plus h minus f of x over h? No, we don't want to do that. We want to now always move on to our formulas, okay? Makes sense, hopefully. Okay. So here's all 6 of our trig functions. Let's kind of group them together. The derivative of a sine is a cosine. The derivative of a cosine is negative sine. So it's almost the reverse of each other, not completely. Okay. Tangent is secant squared. Cotangent, see, it's the word co, has a negative on it. It is negative cosecant squared. Okay. Tangent is derivative is secant squared. Cotangent is negative, the same thing, but a co on it, negative co on it. Every time it becomes a negative co, kind of a reversal thing. It's negative cosecant squared. And then cosecant is negative cosecant cotangent. Secant is secant tangent. Those 6 trig function derivative information, you just have to memorize them. I don't know what else to tell you. Okay. So you just have to have all 6 of those memorized. What's great is if you know the ones without the co. So if you know sine is cosine, tangent is secant squared, and secant is secant tangent, the other ones you just throw on a negative and a co in a way, So like cosecant, look at those compared to secant. You just put on a negative, you tack on the cos. Here, you put on the negative, you tack on a cos. This is the only one where the words kind of aren't, you take off the co because it was a co. I don't know. Anyway, whatever pattern will help you to memorize them. You just have to know what they are. I don't know. It is what it is. Okay. Some facts. If it starts with a C, it's going to have a negative on it. Yeah. I mean, that's a great, whatever helps you memorize that. It's great. Okay. So let's take a look at example 2. It says to differentiate this Uki fraction. And then it says, for what values of x does the graph of f have a horizontal tangent? So let's take care of one thing at a time. Let's take care of the derivative. So we've got this function. It is a fraction that cannot be rewritten in a nice way. It can't be changed. It can't be manipulated much. We're kind of stuck, okay? So what we have to do is when the fraction is stuck as a fraction, you have to use the quotient rule, okay? So the derivative of this is going to follow the pattern. Bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. It's just going to follow that rule. Let me say it again. Bottom times the derivative of the top minus top times the derivative of the bottom over the bottom squared. Use parentheses, use parentheses, use parentheses. Now, there's going to be no way to do this if we don't know the derivative of a secant and a tangent. So we have to know that the derivative of a secant is secant tangent. And we have to know that the derivative of a tangent is secant squared. Okay, so we have to know those facts. So now I don't expect you to know without looking, but we are going to have a quiz, hint, hint, of some very basic derivatives coming up. You're going to have to know these rules by heart. And again, we will summarize them all probably in our next vocab. Okay, so let's do the derivative. Bottom, write it down, keep it in parentheses, times the derivative of the top. We just learned that the derivative of a secant is secant tangent. So it's secant of x, tangent of x. Minus. So the quotient rule has a minus in it. And if it helps you to think that negative exponents are division and there's a minus, I don't know, whatever way you want to think about it, but we have to have a minus at this spot. Then we're going to write down the top times the derivative of the bottom. The derivative of 1 is 0. Now, normally I'm not going to write the zeros, but I want to show you what happened clearly. So the bottom of 1 plus tangent is 0 plus secant squared. All over the bottom squared. Don't usually do anything with the bottom, just put it in parentheses, write it as a square. It is what it is. There you go. Okay. Now, we're done with the actual differentiation. I'm okay with you getting to the first step. Unless it clearly says to simplify, or if you want to check it with your solutions, you may need to reduce it down slightly, but for me, I hope you know how to reduce things. Okay. But the second part of our question said, for what values of x does the graph of the function have a horizontal tangent? The horizontal tangent occurs when our slope of our tangent is equal to 0. We had a question like this, I believe, in the 2.3 notes. So they're really asking when a fraction is equal to 0. Well, fraction only equals 0 when the top is equal to 0. So I'm going to kind of write it like that. Now, how could we make this a little nicer? Well, okay, so first, let's take this and distribute it. Okay, so we get the secant of x tangent of x plus the secant of x tangent squared of x minus the secant cubed of x. Now, every single piece in that puzzle has a secant attached to it. So let's factor, because to find out where this is equal to 0, factorization is our buddy. So you always kind of have to think, is it factorable? Well, when we factor it, we get tangent of x plus tangent squared of x minus secant squared of x. Okay. Now, anytime you see squareds in an any squareds in a trig function, and there's opposite kind of squares, there were Pythagorean identities back in the day. Okay. Now let me over to the side here. Let me write the Pythagorean identities that we know. So sine squared plus cosine squared is equal to 1. So that's one of the ones we know, but that's not helpful in this particular instance. Okay. If we divide through by cosine squared, if we divide every piece of that by cosine squared, we get that tangent squared plus 1 is equal to secant squared. If we divide that original by cosine squared, or sine squared, I'm sorry, we get 1 plus the cotangent squared equals the cosecant squared. Okay. So the one we're searching for is this one. So if you remember, if you only remember this one, we can manipulate it. If you divide through by cosine squared, you get that one. If you divide through by sine squared, you get that one. So we need this one. So if we go back to our original here, this is the only thing that isn't a tangent. Let's take out secant squared. Let's replace it with what it's equal to, tangent squared plus 1. Okay. So in parentheses, I'm going to put tangent squared plus 1. Okay. So I have to distribute the negative. Then the tangent squares cancel out. Yay. And so I get something actually pretty decent. I get the tangent of x minus 1 equals 0. Okay. Now we have two nice things. In order to solve where that's equal to 0, we're going to put that. We're going to put that. We're going to isolate each individual trig function. Now, you may recall that the secant, so here's our cosine graph, that the secant kind of does one of these, something like that, and it bounces off of it. So, you know, it has a bounce up, a bounce down. Is it ever equal to 0? No, it never hits that. It never hits this line, right? So we can just throw this one out. A secant and a cosecant are never going to equal 0. All of our other trig functions do cross over 0 somewhere along the line, but secant doesn't. So yeah, that one's, you know. Okay. Now, let's think about where the tangent is equal to 1. So on the unit circle, over here at 45, or pi over 4, the sine and the cosine are equal. So square root of 2 over 2 divided by square root of 2 over 2 gives us 1. And over here at 5 pi over 4, you also get 1 because you get negative square root of 2 over 2 divided by negative square root of 2 over 2. Another time, you get 1. Now, that's going to happen so you see how these are 180 degrees apart. So every 180 degrees, it's going to get 1 that we want. So how do we write that? So at pi over 4, plus every 180 degrees, which is a pi. So we just write n pi. Let's put n pi. And what's n? N is any integer. So that's the most mathematical way to write. Every pi over 4 plus another 180. So every 45 plus a 180 would keep getting those horizontal tangents. Okay. Now, here's where you can check this, that we're not crazy. Well, you know, maybe I'm slightly, but that's a different story. So if you go into Desmos, and if we type in the function we were given, so if we look at our trig functions, and if we put secant of x divided by 1 plus the tangent of x, here's what we should find. At the pi over 4s, we should have the bumps and the things happening. So let's just test one of them. Pi over 4 is our x, right? That's where our horizontal tangent lies. Negative 3 pi over 4 is 180 going backwards. If we just keep hitting those, all of those end up being a 180 away from a pi over 4. So we're right. So we at least got the right answer, okay? So pretty difficult problem, but we do have all the tools in the toolbox we need to solve a problem like this. Think about the layers that we just needed to know. We needed to know the derivatives and how to take them. We needed to know the algebra to set something equal to 0. We needed to know our trig identities, trig values. So there's lots of pieces and parts to a problem like that, because now it's combining all of these things that we should know. Okay, everybody good with example 2? I know. Let's take a look at example 3. It says an object at the end of a vertical spring is stretched 4 centimeters beyond its resting position and released at time equals 0. There must be a picture somewhere. If you want to look at it, it's in your book. Its position at time t is given by the function you see there. Find the velocity at time t and use it to analyze the motion of the object. Okay. So velocity, it's interesting how our slope of our tangent is actually going to give us an instantaneous rate of change. So if we have a function that tells us position, so one of the first things we need to talk about is that the derivative of a position function is velocity. So make yourself a little note of that, because we're going to use that to help us. So here's a physics application about motion. And that's one of the most common ones. If you take the derivative again, we're actually going to get acceleration. So the second derivative is acceleration. So where 1 would be, in this case, centimeters per second, that would be the first derivative. The second derivative would be centimeters per second squared. It would be an acceleration. Okay, so let's take a look at the velocity at time t. Okay, so if we take the first derivative, we learned today that the derivative of a cosine is negative sine. So this would just be 4 times negative sine, or negative 4 sine of t. So what does that mean? Well, that means if we think about the velocity at time t, that's what this tells us, that the velocity at any particular time follows the negative 4 sine of t motion. And then if we wanted, so that's our velocity. And then if we look at our acceleration, we're going to take the second derivative. So if we do it again, it becomes negative 4 cosine of t. Now it's going to keep toggling back and forth between sines and cosines. It's going to go positive, negative, negative, and then it's going to go positive, negative, negative again. And it'll keep kind of doing that back and forth. So it's kind of interesting how it does that. Think about what we know about the sine and cosine function. They're always sandwiched between positive 1 and negative 1. So the velocity will be no more than positive 4 and no less than negative 4. It's stuck somewhere between positive 4 and negative 4. This means the acceleration is stuck between no more than positive 4 and negative 4. So we can look at what we know there. There's not much else we can say about that. But one of the first things, please make yourself a note, that if we know the position, that our first derivative is the velocity. If we take the derivative again, we get our acceleration. And we'll explore more and more the relationships between those things as we go through chapter 2 and chapter 3. Okay. So this is very important that we know that our position function, if we take its first derivative, it becomes the velocity function. If we take the derivative again, so we could say either the second derivative of our position or the first derivative of our velocity, we get acceleration. If we do it again, I think it's called something called the jerk, and I have no idea physics what that means. but it is a thing, but I don't know what that means. But anyway. So some things to remember. We already wrote these down, but write them down one more time. Every time you write them down, it gets stuck in your brain a little bit, at least we hope. That this pattern, this sine of theta over theta, when we head to 0, is always going to give you 1. cosine of theta minus 1 over theta is equal to 0. So it's just a little fact that you want to know. Okay. We're going to use that fact, and it all becomes because of the squeeze theorem that we can do that. Okay. So here's something interesting. As a result of that, if there's a way to make those match, we can actually find the limit of that. If you try to plug in 0 right now, you get 0 over 0. So there is a way for us to manipulate it. So here's my trick. Okay, just take and multiply through by the reverse of the values 7 and 4 that you see there. So let's multiply through by 4 and 7. Well, no, let's do the one inside. Let's do that one. Yeah, let's just multiply, because then we'd have to do another step. Let's just multiply by 7 on top and bottom. Here's why. If we multiply the top by 7, it's just 7. You just leave it alone. If you multiply the bottom by 7, take out and kind of reverse the positions of the 7 and the 4. So you can see these two mean the exact same thing. I just rewrote them in this particular order. So if I do the limit as x approaches 0 of 7/4 times the sine of 7x over 7x, this part, as long as these are an exact match, always goes to 1. So that means that this is just 7/4 times the limit as x approaches 0 of that matching thing. And if they match, it goes to 1. So that's just an answer of 7/4. Another key takeaway, it is always going to end up being, it's going to always end up being that fraction. You can kind of think of like this goes to 1 and it leaves you that 7/4, if that helps your brain any. It's just kind of a weird little fact. Now, it's a little stranger, I think, to do it for a cosine. Do I give you a cosine one? No, so I didn't. So the one that most often we're going to see or use is that when they're matching on a sine, we can do it. There is a way to do it for the cosine. It's just a little weirder. Okay. So that leads us to our homework assignment. Here's what we're going to be doing. Tomorrow, you're going to have time to work on both your homeworks. Friday, you are having a quiz over some of the rules, okay? Tomorrow, we'll review what some of the rules are. You aren't going to have to necessarily use too many of the rules. I might just give you a list and tell you to repeat what the rules are. Or, I don't know, tomorrow I'll give you more information about what the quiz is going to cover on Friday. So at this time, work on your homework.